And today's subject is light. In fact, dare I call it, let there be light. And who else shines bright in all of our lives but Lynn Koplitz? Lynn, welcome back to Star Talk Radio.
Hello,
You're a
Neil.
founding co-host of mine on this program.
That's right.
And welcome back.
Thank you. It's exciting to be back.
I know. You think about light all the time. This whole show is on light. And what we would otherwise call the electromagnetic spectrum, but it's light to like most people. But to the astrophysicist, light is not just like the colors of the rainbow. Roy G. Biv. You heard of Roy G. Biv?
Of course.
I don't know what you've heard of.
I'm not special needs.
Okay, can you recite them?
Genius.
You're not special needs.
Red, orange, yellow, indigo, blue, violet.
What happened to green?
Well, that's obvious.
Okay.
That's the G.
Right. Red, orange, yellow, green, blue, indigo, violet. That's the visible part of the electromagnetic spectrum.
I didn't know there was a pop quiz.
And then it goes in either direction. So you go beyond the red. Beneath the red, it's infrared. Infra means less than, back when they first laid this out. You can't see infrared. And you go beyond infrared, you get to microwaves and radio waves. We've all heard of these. Maybe you didn't know it was part of the family of light that we call the electromagnetic spectrum. And you come out the other side, beyond violet, what do you find there?
Beyond violet?
Yes.
Headache.
Ultraviolet, and they go beyond ultraviolet, X-rays, and then gamma rays. There's the entire electromagnetic spectrum, and the astrophysicist is an expert in each of these bands, and the universe talks to us in each one of those bands, telling us something different. But what we should do is sort of start off with...
I know, I'm going to be patient, because I don't understand half of what you just said.
Let's start out. Let's see what Bill
Lost
Nye...
me at bands.
Let's see if we can get Bill Nye to just sort of warm us up with just an encounter with what our telescopes do for the universe.
We're on the radio. What better time to ponder what we cannot see? If you start counting, you'd say you see a lot of things. Tiny things like pistils between petals of petunias, and big things like fantastically faraway stars. But now try the eyepiece of an instrument, a telescope. The moon's not smooth. It's a mess. Those aren't just bright dots. They're worlds with rings and weather. Some of the dots aren't just worlds. They're galaxies full of worlds. And so far, we've just talked about rays of light visible to human eyes. It turns out that even though we see thousands and millions and billions of things, we hardly see the energy of the universe at all. Visible light waves, and microwaves, and X-rays, and cosmic rays, even heat waves are manifestations of both electricity and magnetism at the same time. Electromagnetism. It radiates all over the place, or places, all over space, the universe. By building remarkable instruments to detect all these wavelengths of electromagnetic energy, we discovered planets, stars, and galaxies. Now, as we build better and better instruments, we found that we don't know the half of it, actually about the 94% of it. We've detected a great deal of energy from vast reaches of space, but there just has to be so much we don't yet see. Let's look into the sky and stay tuned. For Star Talk Radio, I'm Bill Nye, the Science Guy.
Bill Nye, always telling it like it is. Lynn, welcome with me, one of our guests tonight.
We have cool guests today, and they're all here.
And they're all here in studio. First up in this segment is Michael Benson. Michael, welcome to Star Talk Radio.
Hey, how you doing? Thanks for having me.
How do I characterize you? As like a journalist, a photographer, a photojournalist, a astronut? Because everything you write about and everything you publish books on is about the universe.
Yeah, the answer is yes. That's how you can characterize me. Thank you very much.
An astrophoto-nut journalist.
Astronut photojournalist.
I first met you many years ago. I think you were preparing one of your earlier books called Far Out. Was that one of them, or did I meet you?
No, that was the first one. Far Out is the last one, and that covers basically everything from just at the gates of our solar system all the way to the Big Bang.
Okay, so this is a book where you have collected images together with narrative where you're just bringing the universe to the public. Okay?
Yes. And then the first book was called Beyond, and that's the one you probably saw.
Beyond.
We collaborated a little to put a show up. I don't know if you remember. We put a show up at the Hayden
No, I do
Planetarium.
remember. So Beyond those were the space probes that then put up got images of the planets. So I'm fortunate as an astrophysicist to have journalists who care about the universe, because then you get to do some of the work that we would otherwise try to do, but wouldn't necessarily succeed. And you've been eminently successful at this. Beautiful books that you've published.
Thank you.
So what about the universe attracts you? Is it just because the stuff looks cool? And you're a photographer too, so you think about light and what it does and how it and there's a little bit of artist in you, so you think about how light affects the viewer and
I mean,
images.
I like to think there's a lot of artists in me, Neil, but I'm just teasing you here.
All right.
What about the universe attracts me? That kind of question, it's almost impossible to answer that because everything is the universe, so anything that's attractive is the universe. But what about the universe attracts me? I mean,
Whoa, you just blew my mind socks off. What does that mean?
Oh, my God, I think I did.
No, he's saying even people sitting next to him is part of the universe.
That's part of the universe.
So
okay.
images of him. Right.
Okay.
No, I
my
mean,
universe is just my little universe.
All right.
No, I don't know. It's probably
I'm
quite large.
teasing.
No, but what attracts me to the universe? I mean, I think that part of it, to be moderately serious here, is that in the last 50 years, we have seen things that everybody prior to 50 years ago could only dream of seeing, which is highly detailed images of all the planets, of the solar system, and then also after the Hubble was launched and so on, incredibly detailed pictures of the origin, the beginnings of solar systems in Orion and this kind of thing. So my question is, how is it possible, really, for people not to be attracted?
So when you say beginnings of solar system in Orion, the constellation Orion has one of its stars is actually a region of the galaxy where stars are being born, and that's what you meant when you said
the Orion Nebula.
The Orion Nebula,
yes.
Very famous place in the solar system, a stellar nursery, in fact. And so all these places excite you, and so but you didn't take any of these pictures. You assembled them from public sources, right?
Well, thanks for pointing that out, Neil.
I was just going to say, wow, what a CB, what a blocker.
Yeah, well, no. I mean, look.
So what do we need you for?
Well, I'll tell you.
Why did he even invite you on the show?
I was wondering that too when I got the call, but then I decided I would play along.
Right.
I would play along with you guys.
Mm-hmm.
Part of it is that, it's true I didn't take the individual shots. In fact, it's impossible. No human being has been in orbit of Jupiter, for example, or orbiting Saturn. But what I do
that's right.
do...
Tell him.
Tell it like
Go
it
ahead.
is.
Yeah, tell it like it is,
Pull
Michael.
the gloves off,
Take
Michael.
that,
Don't
Neil.
take that from him.
Take that, man.
He's no genius in here. He's just a guy. I'll hold him. You hit him.
Oh, I don't know. I mean, I think he's certainly
I
got
know.
elements of genius, I mean, just
Well,
the way all of us do.
Pick
But okay.
a side. Pick a side.
I'm on your side, baby.
Okay.
Yeah,
Okay,
it was wise.
let me just say this. What I do is go into archives that have hundreds of thousands of raw images, and I look for extraordinary frames, which I can then mosaic together.
Mosaic means you tile them together and make a bigger picture than what the
Exactly.
single image was.
Yes,
Yeah.
and I composite them to get color, and so I feel very much. I feel almost authorial towards them because some of them really wouldn't exist if I
Authorial.
hadn't. Authorial, like I'm the author.
Oh, okay.
I
Sorry.
feel
hadn't
I
heard
feel like the author of quite a number of them, even though, of course, anybody can go into the archives, and I encourage this very much, to go into the archives
So
of
the
raw
point is,
data.
anyone can do it, but they didn't. You did.
Right.
And so you then had the privilege of being the first in, and therefore the first out with these beautiful books that you've published.
I mean, I'll
It's
tell
like
you a
you
story.
make a collage almost, but you put it
Yeah.
all together.
Yeah, I'll tell you a story. I mean, recently I had a show in Chelsea in my gallery, which is Hasted Krautler Gallery on West 24th Street. And because I had the deadline of February 3rd to have an opening, I went into the archives and I started digging in Cassini material. Cassini is the spacecraft orbiting Saturn right now. And I started looking for extraordinary images.
Tons of
recent
images are there.
Yeah,
Mhm.
and I found these amazing images of the dark side of Saturn, which was not dark. It was not dark because there's so much indirect light bouncing off the rings and so on. And I put together a multiple frame mosaic. And as it emerged in color and I made it seamless and everything, I had the very real sensation that I was the first human being to see
the backside of Saturn.
You can put it that way. The back side of Saturn. I saw the rear side of Saturn in a way. And I had this amazing sensation that, I was a privileged person because I had done this. And then, of course, for me, part of the fun of it is to get it out there and And show it to people.
Let me bring in my second of
It's
three.
beautiful.
It is. Let me bring in my second of three guests. His name is Brian Abbott. Brian, welcome to Star Talk Radio. Your first appearance.
Thank
Correct.
you, Neil. Thank you. It's a pleasure to be here.
Brian, you have to tell this to the audience. Tell everyone, because I know in advance. Tell everyone what it says on your business card is what it is that you do. You are what?
Well, I have a business card that reads Manager of the Digital Universe.
Manager of the Digital Universe. That is so cool. That's like, does that get you dates in the bar? Is that?
It doesn't hurt.
It's better than Staple. Manager of Staple.
So Brian, you come to this. You have a huge science background. You're computer literate, and you put together data sets for the Hayden Planetarium that enables people to sort of take journeys through those data. And so, what are some of your challenges collecting them scientifically? Because Michael Benson is mining the archives, and that's cool. But at the end of the day, they're still just photographs. Photographs, 2D photos. Sorry, Michael, I'm sorry. So, Brian,
It's art, too.
Yeah, it is art. It is art. But, Brian, you take another dimension here. So where do you take it?
But that's just another dimension.
And that's a hard dimension. You know, astrophysicists have a hard time getting distances.
Distances is
Taking
everything.
Pictures of something in the night sky, seeing the sort of 2D sky, if you will, from Earth is great.
What
but
sky? Oh,
the
2D.
two-dimensional.
2D. Mm-hmm.
But getting distance to that object is very challenging.
And once you get the distance, then you can create a journey through it, right?
That's right.
Okay, so now it's not just visible light data that you've got, because we've got telescopes in every band of light of the electromagnetic spectrum. We have ultraviolet telescopes and infrared. We got a telescope in every band that we cannot see. So what do you do with those data?
We show them.
How do you show them if we can't see them?
Well, that's the challenge.
Actually, I know the answer to that question, but I want you to say it because you've got the title Manager of the Digital Universe.
How do you reconcile showing something that we should be seeing with our eyes, visible, like the stars in the sky, with something that is invisible to our eyes?
That's what I'm asking.
Like?
How do we
Yes, thank you, Lynn.
What's invisible?
Like microwave radiation or infrared or ultraviolet.
Right, so how do we see that? How do you make it visible to us?
The scientists, and we take, and our third
You're the
guest
manager.
here.
You're the manager. I want to see the manager on this.
I want to see the manager. I want to see your manager.
Take me to your leader.
For real, I want to know.
We essentially decide how it looks. You get a sense of how it looks from the instrument, and then you decide how you want that to look. And that relates to how we see things as humans. So it's always a judgment call.
So you're converting invisible light into light that we can see, but then you have to be honest and say, you actually can't see this. This is what it would look like if you could see in those bands of light, correct?
Exactly, yes.
Like when they tell you this is how a dog sees things. You don't really know that.
I guess not. But you can study.
Yeah, but somebody has to decide what would it
Somebody's
look
got to make
like
that judgment.
on the scientific data that they have.
Somebody's got to make that judgment.
Brian's the guy.
Exactly.
Then you need to make a dog hearing simulator or a dog seeing simulator.
Right, which is
You're that
essentially
guy?
that's essentially what
That
you've
guy
done,
with the
Brian.
universe, yes.
You've made a simulator that allows us to see in bands of light we cannot.
Correct.
And so what's your favorite data set in a band we can't see?
Well, I love the W map.
The W map. So this is of the microwave
This is the microwave radiation.
of the entire universe.
The baby picture of the universe.
Of the universe, born, the light cast forth.
13.4 billion years ago.
So you just digging it.
So the Big Bang picture, like when God said, "Let there be light,"
Baby
you're
pictures.
like what it looks like when it turned it on.
Well, it's as far back as we can see.
I know. I'm with a room full of scientists. Oh God, what does that mean?
Stairway to Heaven, for example.
Michael Benson, journalist, photographer, space geek all the way. And not a month goes by where I don't read one of your op-eds or editorials criticizing NASA and the nation's priorities. Maybe we'll get back to that a little later.
Wow, there is some weird tension with you guys.
Brian Abbott, manager of the Digital Universe at the Hayden Planetarium. Thanks for being on Star Talk. And, of course, my inaugural co-host, Lynn Koplitz.
There's weird tension between you two.
the light of your life.
Well, yes.
Second light.
So we are here talking about Let There Be Light, the light of the universe, and how it's created, what it's all about. Let me just sort of reset some of the physics of what's going on here.
I have some questions.
Sure. So light is energy. It's a form of energy. There are a lot of kinds of energy. There's kinetic energy of motion. There's potential energy. You get that in where you are in the universe. Or you can have chemical potential energy. That's the energy that shows up when a bomb explodes. But in the universe, light is a form of energy, and we call it electromagnetic energy. And
that's from the Big Bang?
Yeah, so at the Big Bang, you have all of this energy in a very small volume, and it is so hot, it is so energetic that matter is forming out of the energy according to E = MC squared. And the matter that's
according to the Bible, God just said, "Let there be light," okay. And then the light turned on. But you're saying
yes, I'm saying something
bunch of crap
different
together.
from that.
Okay.
I am indeed saying something different from what you read in Genesis. Yes. So what we have here is this soup. It's a matter-antimatter energy soup. And then as it expanded and cooled, all the matter and antimatter particles collided with each other and annihilated and created light. Except some matter was left over out of this. 1 out of 100 million particles was left over, and that is the matter that you and I are made of. And all the other matter-antimatter collisions, the light of the universe, now visible as microwaves. At the most distant regions of the universe, we call it the famous microwave background, the baby picture of the Big Bang. And so this is light. It all travels at, of course, the speed of light, which in miles per second, 186,282 miles per second. And if you want to get really geeky at home, one nanosecond, that's a billionth of a second, light travels 1 foot. So if you're standing a foot away from someone, you can say, "I see you not as you are, but as you once were a billionth of a second ago."
So if you were going to time travel, would that be the speed of light, like in Back to the Future?
Will it be exactly? Yeah.
I like my really serious questions. Look at all of our science, all of our really smart people in the room. We're like, who is this hooker and why is she in
it's
here?
exactly like that, minus the flux capacitor. Yes, So telescopes are kind of like time travelers because as you see far out in space, you see far back in time. I see you as you once were, like I said, 2 billionths of a second ago. You're 2 feet away from me. You are younger as I see you than you are at that moment that I see you. Yes. Yes. The moon is like a little more than a light second away. The sun 500 light seconds away. We have galaxies. Here's a cool one. We have galaxies that are 65 million light years away, which means if they had a powerful telescope, they could look to Earth and they can see the dinosaurs going extinct as it's happening, as it's unfolding.
You're blowing my mind.
They would need super duper telescopes for that.
Can we go back to something simple for a second?
Well, what's that?
Because let's break it all down for me. Okay.
Yeah.
First of all, like you said, light and energy. Is that why we can see lightning?
Well, so lightning is a lot of energy in a small spot, which rapidly expands the air, and it creates basically a shockwave, so you hear the thunder, and it's it rapidly expands the air, and it's a shockwave, okay, and so that's why you hear it. And, of course, you hear it later than you see it. But it is very high temperature, and when you bring anything to high temperature, it glows. You see the sun, because it is at a high temperature, it glows. You heat anything to high enough temperature, it will glow, period. Whether or not it's a gas, solid, it'll glow. That's correct.
How interesting.
And there's a guy from the 19th century who put together all our current understanding of the behavior of light. And he's called Maxwell, James Clerk Maxwell. And they're called Maxwell's equations, one of the most beautiful set of equations there are in all of physics. Have you ever heard of Maxwell?
No. You know, the only Maxwell I know is
checking.
the coffee guy.
No, I'm just checking. In fact, I don't know if it's the same guy. Probably not, though. My guess.
Who discovered X-rays?
Who discovered X-rays? Wilhelm Röntgen. In fact, in Germany, they're not called X-rays. They're called Röntgen rays. Yeah, so they still.
Rays?
I don't know if I'm pronouncing any Germans out there.
Thank for my mammogram.
Yeah, basically, Wilhelm Röntgen. And was actually discovered quite by accident. He was working with sort of high-energy emissions from tubes, and his hand happened to be in the way of a photographic plate, and he developed a plate and saw his bones on that photographic.
That's creepy.
It's completely creepy. I would have freaked out if that had happened. And so
then he did it again?
Not knowing that this is the kind of things you die from, too much exposure to X-rays. You've been in the X-ray room, and what does the X-ray technician do right before they flick the switch?
They all leave.
They leave, close the door, shut the door, That's what they do.
The CAT scan's the worst. They go to, like, down the hall and talk to you through a thing. They're like, are you okay? No, I'm not okay. I'm alone in, obviously, what's a really frightening room. Well,
these are just bands of light that actually are in our everyday lives. So your cell phone uses microwaves.
Tell me this, because and now I've got all of you here in this little light summit meeting. I want to know when, like, I travel all the time when I'm on the road, and I'm going to be doing it this week. Wednesday, I'll be at the Orlando Improv. Okay. But anyway, my question is this.
And for those who are listening on Time Delay iTunes podcast, which Wednesday was that? Yeah, that Wednesday's like a month in the past by then. Okay.
Somewhere in June. Whatever. Just go online and look for it. But the Orlando Improv.
It's a light delay.
But here's my question. They're making me now at the airport walk through those body scan things.
Yeah, that's where someone else sees you naked, and the person that sends you through doesn't see it. They try to split the person who knows who you are from the person who sees your body parts.
I don't care about people seeing me naked. That is enough of that. If someone wants to say, by all means, they can take a look. But I'm more concerned. Like, can it kill me? Like, how? Why does this light hurt us?
I haven't formally studied that scanning process. And
so you don't know? That means DK in genius speak.
What they don't know. Yeah, so they claim that it's not any more dangerous than a plane flight that you might be taking. Your exposure to radiation on that. Brian?
This is exactly what I've heard. That when you fly in a plane, you're actually exposed to more radiation than you would be on Earth.
Right, on Earth's surface, because the atmosphere protects you it shields you from a lot of radiation that's coming from space.
Exactly.
That's right. And notice that the doors of it are open. By the way, in your microwave oven, which also uses microwaves. By the way, I should have led off by saying, what's the difference from one band of light to the other? The length of the wave itself. Microwaves are about a half an inch, a third of an inch long in a little wave shape. So if you want to block microwaves, just put a screen where the mesh is smaller than that size, and the microwaves can't get out. So take a look at the door of your microwave oven.
Got that screen.
It's a screen that's got holes. Why doesn't the microwave come through the holes? Because the wavelength is bigger than the holes themselves. And are you old enough to remember how people used to receive TV signals? Rabbit ear antennas? Yeah, exactly. Why are the antennas that long? They're about a meter long, about a yard long. That's the length of a radio wave. Radio waves are longer than microwaves. And you want to capture radio waves, you get the antenna has to be about that length. So walkie-talkies, which use microwaves, how big is their antenna? It's much stubbier. It's like, it's like an inch.
Wait, if they use microwaves, then can't that be bad for you to talk into them?
Well, if you create a cavity and zap you with much greater power than what goes on in a walkie-talkie, then it would boil your blood, and that would be bad. Right?
Yeah,
but that's not what happens otherwise.
Microwaves cook things from the inside out,
Yeah,
right?
so microwaves, what happens is the water molecule really likes microwaves. They have a deep, cozy relationship with each other, which is one of the reasons why when we try to observe the universe in microwaves, you want to get above the cloud-forming layer of Earth's atmosphere because clouds wreak havoc on microwaves. Your cell phone signal is worst during thunderstorms. And all microwave signals are corrupted in the presence of water. And we exploited that with microwave ovens because most food that you'll ever consume has water in it, and the water absorbs the microwaves. It vibrates real fast, and it's friction that cooks your food and nothing else. And so people who think of microwave ovens as nuking the food, not. It's just the vibration of the water molecules all next to each other, vibrating ferociously, creating heat. And it's microwaves in our life and in our culture. And microwaves, Brian, you've got microwave data sets telling us what's going on in the early universe.
That's right.
What kind of light is it in night when you use night vision goggles?
It depends. So the kind that you flick the switch on your camcorder, that one is like infrared.
No, but that's night mode. I'm talking about the kind Buffalo Bill wore in Silence of the Lambs.
Oh, okay. So that would be like an image intensifier. So that takes the very low. Those are developed in wartime, by the way. So you can shoot people in the dark of night.
Like what the SEALs use.
A lot of this is military technology. And so very, very low light situations, you can greatly magnify it electronically. So it looks like it's broad daylight to you and someone else is groping in the dark. So
groping? Do you mean that literally?
Mean what literally?
Groping? The groping.
Yeah.
I'm just trying to make an intervention
Mike's
here.
getting a feel for the show.
Yeah, getting a feel for the show.
So Mike, on any of your photos, do you have a relationship with other bands of light? Or you primarily visible?
What kind of relationship do you mean? No, no. I'm going. I'm trying to stay with visible spectrum.
So you're a visible
images.
guy.
I'm a visible light guy.
That's okay. But you realize the human eye sees in 1 octave of light, and we have detectors that see in 64. So what you're telling me now is that all of your books basically are demonstrations that we're actually mostly blind in the universe.
Oh, but we're mostly blind in the universe anyway. I mean, 99.9% of the universe is made out of stuff we don't even understand.
That's a whole other...
I can't believe I have to tell you that.
point of ignorance going on there.
Speaking of ignorance, I have another question.
Oh, you have another question? We might have to save it for the third segment. Get it in real quick. Go.
No, I want to ask about photosynthesis.
Oh, cool. Yes, we can so go there because plants like light. I've got Michael Benson, author and journalist. I've got Brian Abbott, manager of the digital universe at the famous Hayden Planetarium here in New York City. And, of course, the light of Star Talk, Lynn Koplitz herself.
Hello.
Lynn, you had a question just before the break. What was that?
I did, but I have to tell our guests that Neil tells me there are no stupid questions, although sometimes I feel uncomfortable because I do feel like there are things I should have listened to in science class.
Let me just say, you asked the best stupid questions there ever
thank
were.
you.
Okay.
Okay.
If that's how you have to feel about it.
Having preempted that, I will say, I've now... I never used to be able to let plants live in my care, and I've just started raising some little plants, and I've given them all names, which is kind of weird, but I'm 43 and
you've named
single.
your plants. Okay.
Yeah.
Right.
Anyway, so I put them on the fire escape, and they're doing quite well. But I've noticed, because I've been home, I haven't been on the road for a month or so, and I've been able to watch them, that, I know that photosynthesis is what it is, right?
Yeah, they like light. Yes, they need light.
But some of them, like Steve, he's foliage. He leans toward the light.
Steve leans.
But what I thought it was
Steve
just
is the name of
sunlight.
one of your plants.
Yes, but here I thought it was just Steve he's very cute. But Steve leans towards the light, but I thought it was just sunlight. But I bring him in at night.
Any light that so
any light. And the pansies open up at night when I turn the little light on at night.
So you're messing with their biorhythms.
Well, that's my question. Am I screwing them up?
Is pansy the name of a plant, or is that the type of plant?
Their name's Panzel, Michael.
Oh, okay. Well, I should have known.
Why would you name them pansy? They are pansies.
Duh. So
be like me calling you man.
Most people think that plants like light, but in fact, it's the light that's inhibiting the growth of the plant on the side of the plant that faces the light, allowing the far side of the plant to outgrow the side of the plant that's nearest the light. And so we then say, oh, it's leaning towards the light. In fact, the light is inhibiting the growth of the plant on that side.
Oh, no, I'm stunting their growth.
No. Well,
this is why I can't have children. Because I don't know how to take care of
I don't see that connection. I'm sorry.
Because I could stunt their growth.
Yeah, because you have to do more than just water the children. Yes.
But here's you have to do more than just water a plant. Here's my question. So when it's leaning, then why does it say to plant things in direct sunlight?
There's some plants that prefer direct sunlight rather than diffuse sunlight or indirect sunlight. So it just depends on how the plant evolved.
So if I don't have sunlight, can I just put them in a pot and put a regular light on them?
If you want a light that's close to the spectrum of the sun, and you can buy sun lamps. Oh yeah. But you can completely. You don't even need the outdoor sun. Just go for it.
Interesting.
Yeah, just put in a light that you don't want a regular incandescent bulb. It's not blue enough for what the plant would
What happens to people
on.
if they never have any sunlight?
Vitamin D? What's the vitamin you're supposed to take in the winter?
Vitamin D, yeah.
Yeah, so you don't get vitamin D. You don't produce vitamin D.
Yeah, if you have light skin, yes, that's a rule.
So what happens to you?
Well,
can you die from not getting any light?
Get scurvy.
Yeah, no, scurvy is vitamin C. You
okay,
get your
but
vitamin straight.
Improvising.
Are you like powder?
So you need the sun helps the body produce vitamin D. That's correct.
But what happens if you don't have vitamin D? What happens to you?
Your bones weaken.
Really?
Yeah, and if you
get depressed
and
if
you're developing, then you get rickets.
I think I have that.
You look like the cowboy with the bowed legs.
Okay.
But let's get back to the universe, if we may.
Please.
Just let's understand how this works. So we have objects in the universe that emit light, and the visible part that's easy to understand because our eyes see visible light. Many really cool things in the universe don't know anything about visible light, and they're trying to talk to us in bands of light we cannot see. And it's a triumph of 20th century astrophysics that we've been able to build specialized telescopes with detectors that can reveal the universe in all these bands of light, ultraviolet, X-rays, gamma rays, radio waves, all these bands of the electromagnetic spectrum that tell us what the universe is actually doing, because we are practically blind.
Who came up with black light?
Black light, that's just ultraviolet light. And the part of the ultraviolet light, the part of the black light you see is just violet. But it's really doing its job in the part of the spectrum you can't see, the ultraviolet. And bug zappers?
Oh, that's right, because the ultraviolet, that's right, because black light, you can see all the lint and all the dust.
Yeah, well, so that's the ultraviolet sort of rendering that aglow. So
Is that what you used to find DNA on things like the crime scene people use?
The crime scene people will use ultraviolet light to see different things that might be left on your sheets, yes.
Interesting.
And a quick thing about bug zappers. Did you know that bug zappers are violet, basically, because bugs just love violet light? They come out in the early evening where the sky has a higher fraction of the total light represented in ultraviolet. And so you simulate the twilight sky with a bug zapper, and the bug says, I'm flying to the light, and it just gets zapped.
Oh,
and it's great. It's evidence that we're smarter than bugs, that we can exploit the fact that they are sensitive to ultraviolet light, even though we're not. I got to bring in our third guest here. This guy, there's no one like him in the universe, last I checked. Carter Emmart. Carter, you are Director of Astrovisualization of the Rowe Center for Earth and Space. Welcome to Star Talk Radio. And you just gave a presentation at the World Science Festival last night, bringing the universe to the public as never before. You were born an artist with deep interest in the cosmos. You became computer literate, and you transitioned what used to be canvas and paint for planetarium shows into the 21st century. So welcome to Star Talk Radio. And tell us what you did last night.
Thanks a lot, Neil. Yeah, actually, at the Hayden, we had a program that was looking at, it started off with a 60s era light show from the Joshua Light Show. And then we went in.
60s era had lasers and stuff, right?
Well, no, it was pre-laser.
Pre-laser light show.
This is, and the Joshua Light Show actually backed up Jimi Hendrix and other bands.
So were people getting high in the dome at the time?
Well, 10 minutes of that, and then basically I took us in a piece where we go from the Earth on out to the cosmic microwave background.
So
we
you
go
zoom,
back in time.
A powers of 10 kind of zoom.
Yes, we do, and then we actually travel all the way back to Earth and through the atmosphere and down to the town of Norrköping, Sweden, where I actually directed this film last year, and we fly all the way down to quarks in a carbon nucleus.
So these are Swedish quarks, apparently.
Yes, in that case, it's a strand of DNA.
So as you zoom out, there'll be some familiar things. We'll see Earth from a distance,
right.
Like the Apollo images. But rapidly, those images would become unfamiliar because you're zooming through a three-dimensional space that telescopes can't provide.
Yes, but it's a data map. Thanks to my work with Brian. Brian taking data sets, academic data sets, catalogs of various objects that we see, we observe with light, and their signature from the light gives us distance information. We're able to plot that. And
in three dimensions.
In 3 dimensions. A revolution in planetariums really occurred from that of showing the sky to now showing space three-dimensionally.
Lynn?
I just have a question because we're talking about the universe. It's just so humongous. The idea of like you creating a light show that represents certain part. How do you decide exactly what you want the show to be? Like it's hard enough. Like when you're putting together a musical or something, how do you decide what parts of the universe are interesting and how you're going to use them?
Or another way to say that: how do you know what to not include?
Exactly. That's what I'm trying to ask.
The idea of the digital universe is to include everything. And
that's a cop-out. I mean, it's the right answer, but you choose a pathway to take the visitor on it.
Yeah,
and you're invoking an artistic eye to this.
We're also, yes, and design and movement is a big part of it, and that goes to the heart of what our space shows are and how we create them and how to display the data.
Because a pure scientist wouldn't necessarily know the best way to look at their own data, right? And you have an artistic eye for this.
Well, and also it's a matter of putting the pieces together. If you look at any one data set, say stars, that'll be very interesting to the people that study the stars. But to put that in coordination to our solar system or the galaxy at large that those stars are part of is our job.
So now you get the whole sweep of the universe.
That's right.
So Lynn is the whole freaking universe.
So also, I should say that the program last night, after bringing us back down in light, essentially from the most ancient light we can see, which is the cosmic microwave background.
In microwaves, yes.
Because as we look farther out, we're looking farther back into the past. That as we come down, we then hand it over to Joy Hirsch, who's the director of the Columbia Brain Lab, and she talked about really the difference between photons and essentially the light in our mind in a sense of understanding. And so we're really trying to address this issue of the universe around us and the universe that we know in our brains.
So you went from the outer universe to the universe of our inner mind.
Correct.
Good.
You know what that reminds me of? When I was in college, I took a lot of drawing. I was like a art minor, and I remember one of our teachers telling us to squint our eyes, because what we thought we were seeing and what we were seeing were different things. And he said, if you squint your eyes and you just draw the shadows and draw, the shadows and the light, and then it was so weird because you look up and all of a sudden you have a whole image, and it's what you were really seeing.
Yeah. So Brian, how do we know? I mean, how do you distinguish? I mean, both of you, Brian and Carter. So there's what is, and there's what our perception is. And how do you make the two work to get the most effective show?
Well, when we look up and we see stars, we can sort of have a sense that they're different distances. But to really see the layout and the distances, or say where the planets fall in this, because look up in the night sky tonight and you'll see one of those bright stars, so to speak, is Saturn.
It's Saturn in
so
the evening sky. It's a beautiful sight tonight.
And we were showing that with the World Science Festival just on Friday night, which was wonderful. And people always
right under the Brooklyn Bridge. That was a beautiful setting.
Yeah,
if people don't know, this time of year, every year in New York City, there's the World Science Festival, and some of the greatest scientists in the nation and in the world descend on New York and bring science to the public in many different venues, one of which was the Hayden Planetarium last night.
But if you look at the grand tradition of natural history museums, you typically have a diorama. So you'll have taxidermied animals, and then you'll have the grass or a tree, and then you have a backdrop painting, which is too far to really discern some depth to. So in a sense, we have a digital diorama of the entire universe.
Cosmic diorama of the universe itself. You can follow us on Twitter. Star Talk Radio is our handle. We're also online, startalkradio.net. And, of course, you can like us, Star Talk Radio, on Facebook.
That sounds needy.
I like you, Neil.
Brian Abbott, manager of the Digital Universe. You had some comment just before the break about the difference between how a scientist views data and how you guys make it alive.
Yeah, what struck me when I started working on this project is that scientists see their data not only as a 2D graph, but also they only see their data. They don't see it in the bigger picture, the bigger context of where that fits in the universe.
So they're visually
2D is in two-dimensional, right?
Yeah, of course. Yeah.
This is 2D.
So they have a
Sorry,
narrow
it's not
view.
2D, tutti frutti. 2D, yes, 2 dimensions, yes. So it's a really boring way to look at the data, and you might miss the bigger picture.
Yes.
And so, Carter, you make the big picture is what you do.
Right. The scientists understand the bigger picture, and that's their job. And it's our job to, again, create that continuous experience from Earth all the way out.
One of the most moving moments in this journey is when we pass by the radio bubble. Tell us real quick about that.
So, yeah, if you actually look out into the stars, you can say, okay, they're different distances. But if you stand away from the Earth, let's stand away from the Earth about 100 light years, you would look back and you'd see a sphere about 70 light years in radius.
That's if you had radio-sensitive eyes, you'd see a sphere.
No, you'd have to actually be detecting it and be at the sphere,
At
essentially.
the sphere, okay.
But what we do is we draw a graphic of a sphere, and that indicates how far radio signals have traveled since the Earth became radio bright. You had Tesla and Marconi and early radio that bounced around inside the ionosphere.
So it's not when Earth became radio bright, it's when human beings on Earth became radio emitters, right?
Yeah, that's right.
With their apparatus.
With radars and television carrier waves. And so you can see that moving out. So if you parked next to Arcturus tonight, which is up in our sky, you would
let's plan to do that. Yeah,
you would be hearing radio broadcasts or TV from 40 years ago.
Yeah, see, I have that question. If there's all this stuff that we can't see, all these waves and light waves and things
penetrating your body right now,
then don't they all bump into each other? When is there too much, and what happens?
Yeah, no. The interesting thing about is they can interfere, but they only interfere if they're sort of coherent. So a laser, you can make lasers interfere, and you get like what they call fringe patterns.
Oh, before we leave, I have to know: are there lightsabers?
Oh, you mean
in
like
real
in
life?
Star Wars?
Yeah.
No. Okay. So now. So,
he told me to wait and ask on the air.
No. Here's the thing. No, you can make a beam of light that would be visible, such as lightsaber.
Like your light beam thing that you use to point.
And I even tweeted this a few weeks ago. Lightsabers would not hit each other; they would just pass right through one another, and they wouldn't have these sword fights the way they would show it. They would just pass through one another.
What kind of light is lasers made out of? Like
it's visible light. You can make other kinds of laser light, but the ones we're most familiar with are visible.
The radiosphere sort of sets us up in a sense that if you go away from the Earth far enough, you're going far enough back in time. Everything we see, a star twice the distance away is twice as far in the past, essentially. So if you look far enough, you're actually seeing the cooling off of the universe, or the transition between when it was a plasma and opaque to where it became clear space. And that's the microwave background that we see.
So you not only show us the
around
radio bubble that we created, that's now about 100 light years out.
Right.
And all of our civilization, as we've communicated it through each other,
That's
has
right.
leaked into space and is contained within this bubble.
So you
That's
show
right.
like if God were to look at it.
Yeah, but those
or
are
Carter, yes.
those are waves moving out, our radiosphere.
Mm-hmm.
But the stuff that's coming to us is essentially, you can imagine a sphere, very large, that's a microwave background, and everything that we can observe is contained within it. And it's centered on us, but that's just because it's us observing it. If you moved anywhere else, you'd also see a sphere
You
around
would feel like you're in the center of that. So now we're in
Carter creates like accurate art.
Yes, and that is the hallmark
Scientifically accurate
of the
It's
21st
pictures
century.
from data. So,
That's and like he gave the analogy a moment ago with the dioramas, something that the American Museum of Natural History pioneered 100 years ago, where you create. It's not just an animal stuffed on a pedestal. You put it in an environment that transports you to that local to that
so
location.
Cool.
Yeah.
So now we're in an expanding universe, and this microwave light and all the light in the universe is getting diluted in space, and its energy is dropping, and so the universe. I don't know if you knew this. Is approaching. The universe will not end in fire; it will end in ice, not with a bang, but with a whimper. And
I saw that movie.
Yeah, well, it's a poem. It's a T.S. Eliot poem
Heat
as
death.
well. So they call it a heat death, but it's really a cold death.
How do you equate that with global warming, Neil?
Yeah, so.
I mean, I don't know. I mean, does that mean that you don't believe in global warming?
Earth
Neil?
is insignificantly small compared to the scale of the universe on which I'm referring. And so the temperature of the universe, of this cosmic microwave background, you can actually stick a thermometer in it and get a reading. It's about 3 degrees absolute temperature. 3 degrees above absolute zero. So, and we're about 14 billion years old. When we're 28 billion years old, we'll be 1.5 degrees. And it'll scale right on down until we asymptotically approach zero. And the day will
Really
come.
asymptotic?
Yeah, well, as you approach it without ever actually hitting it. You get closer and closer without touching it.
Everyone just looked at you like they knew what you were talking about. I'm like, asymptotic.
Asymptotic. You learn that in Algebra 2 and trigonometry.
Oh, okay.
In high school. Yeah. So
Skipped it.
So all I'm saying is that the temperature of the universe will continue to thin out and get cooler and cooler and cooler. Stars.
Is that bad?
Well, yeah, I think so. Yeah.
Sounds bad.
Stars will eventually run out of their fuel. They will die. Even the clouds, they'll make whatever stars they can, and then they'll die out, and then all matter will be left. Will be left in the remnants, the dead, cold remnants of stars that once were.
The universe sounds feminine. It sounds like women. Like you have to work really hard, and then the Earth is just men.
Well, once these
around.
energy sources run out, the stars will turn off one by one, the galaxies will shut off, and the universe will turn dark for the remainder of eternity. Brian, how can you say anything after what I just said?
Downer.
Well, it's fascinating that future astrophysicists will not know anything about cosmology because they will not see any of the galaxies out past our local globe.
Oh, because we will expand so fast that our galaxies will expand beyond the horizon.
But that's not true, because if you look far enough away, you will see some of that radiation coming toward you.
Well, it's yeah.
By
that's another show.
By then we're going to have faster than light travel, and we'll have sources. We'll be able to make our own stars, and we'll be able to zap.
And Michael
around
Benson's been reading tons of science fiction lately.
Of course.
Yes.
I mean, come on. Let's not be so grim. We'll fix it with.